Morning, everybody. All right. Everybody have a good break? Yes? No? Okay, good. So today we're going to get into chapter 17, and I went off and forgot my laser pointer slide changer thing, so I'm going to have to stay fairly close to the computer today. So we're going to start talking about carboxylic acids and their derivatives in this chapter. So describe for me what you know about carboxylic acids. Let's start with the most obvious. They're acidic, right? Are they strong acids? As defined how? By their pKa value, okay. So when I place a carboxylic acid in water, it completely dissociates then into its ions. What's the pKa of a carboxylic acid? Give me a range for a typical one.
30.
For a carboxylic acid? 30? Lower than a typical acid? 15 to 20? What's the pKa of water? So you think of carboxylic acid as... What happened? We are not even close in the ballpark. We are playing baseball and y'all are on the football field here. Where are we at? 4-ish. Yeah, all right, so somewhere in that ballpark. Right, somewhere between 3 and 5 is for a typical carboxylic acid. So let me ask again, is it a strong acid?
Yes.
As far as organic molecules are concerned, the answer is yes, but is it a strong acid? No. When we place a carboxylic acid in water, a typical one, they do not completely dissociate into into hydronium. Okay, they are by and large weak acids. But when we look at the spectrum of organic molecules, right, they're quite strong. Right, a typical hydrocarbon, the CH bond, right, has a pKa of around 50 for an alkane. Right, and then we go down to about 45 for an alkene, down to 25, right, for an alkyne. Remember those rules, right? So there are things that affect acidity, okay? So we're going to talk about things that affect their acidity today a little bit, because not all of them are in that 4 to 5 range. Some of them actually are quite strong, okay, depending on what the carboxylic acid functional group is attached to. So in an IR spectrum, what would the IR spectrum of a carboxylic acid look like? What two things would I be looking for? I'd be looking for the OH, and does it look like an alcohol? Does not. It's a little broader, right, and goes into the CH region. And I'd also be looking for what? I'd be looking for the carbonyl, somewhere between where and where? Nope, too far. 1,500 and 2,000, right, somewhere in that range, okay? So that's what we're going to be looking for, okay? So you'll remember that a carboxylic acid, right, is a carbonyl with an OH. And remember that we call this group a carbonyl attached to some R group. That's an acyl group. When you all get into biochemistry, you're going to talk about acyl transfer reactions. They're extremely important in biology. Okay, this is how your molecules signal each other. They actually do chemistry. It's not biological magic. It's actual chemistry occurring, right? And you'll talk about enzymes that do acyl transfers. It's a very important class of reactions in biology. And that's where the name comes from. So they are taking a carboxylic acid derivative that is biologically compatible, and enzymes are doing chemistry with it. Okay, now carboxylic acid derivatives, we can change the Z group. If it's OH, it's a carboxylic acid. But if it's some kind of OR group, it's an ester, right? If it's a nitrogen, we've got an amide, right? Where are amides important in biology? Amino acids. This is how amino acids are linked together to make biopolymers that we call peptides and proteins, right? Very important. Okay. We also have anhydrides as a derivative of carboxylic acids. What does this look like? Where did we come up with the name anhydride? What does that mean? What does "an" mean, Anna? Means without. So your name is without na. I'm just kidding with you. What does anhydride mean? All right, we're talking about minus water, basically, anhydride. Okay, so if you look at this and if you think of this molecule as something without water, what would it be without water? If I added water to it, what would it be? Would be hydrous, that's true. If you take 2 carboxylic acids and remove a molecule of water, you get an anhydride. So this is like one carboxylic acid. This is like the other carboxylic acid. If you add water to this molecule, you actually get 2 carboxylic acids, okay? These anhydrides are actually quite useful in organic chemistry. We use them all the time to do acyl transfer reactions, okay? You can react an anhydride with an amine and get an amide, for example, okay? So you can kind of mimic biological systems using these anhydrides. They have very similar chemistry to the acid chlorides, but they're less reactive. They're a lot easier to work with, okay? Now, this is a symmetrical anhydride. Where is the plane of symmetry? Through the oxygen. The left and the right-hand sides are identical. This is what we would call a mixed anhydride. Why is it mixed? 2 different R groups. It actually comes from the condensation of 2 different carboxylic acids. This is the same carboxylic acid removing water from it to make the anhydride. This is actually 2 different carboxylic acids, okay? Some people not only call these mixed anhydrides, but unsymmetrical, obviously, for the obvious reason. There's no plane of symmetry through the oxygen, okay? And this is a cyclic anhydride for the obvious reason, right? It is part of a cyclic molecule, okay? So we have symmetrical, mixed, and cyclic. The cyclic one is also symmetrical. Are all cyclics symmetrical? No. It's not necessary that they be symmetrical, but this one just happens to be, okay? Various types of amides. We can have primary amides, secondary amides, and tertiary amides, right? Looking at the number of nitrogen-carbon bonds. So here we have 1 CN bond. Here we have 2 CN bonds, and there we have 3 CN bonds. And so we have primary, secondary, and tertiary amides. Okay? We also have cyclic esters and amides that you need to remember. We've already talked about these a little bit, right? And when we were talking about functional groups. This is an ester, right? But it is a special type of ester because it belongs to a cyclic structure. And we call these lactones. A lactone is nothing more than an ester. A lactone has the same chemistry as an ester. You can form lactones almost the same way as you form esters, okay? And so we have a cyclic lactone. This is called a gamma lactone. If you start at the carbonyl carbon and go out to the alpha carbon, beta, gamma, you can see why it's called a gamma lactone. You're counting the number of carbon atoms between the carbonyl and the oxygen atom of the ester, okay? So alpha, beta, gamma. This is a delta lactone, alpha, beta, gamma, delta, okay? So you can have all different types of lactones, and the Greek symbol tells us how many methylene units, or carbon atoms, I should say. They're not always methylenes, but carbon units that are between the carbonyl and the oxygen atom, okay? So it's just counting on the Greek alphabet. We can also have cyclic amides. We call those lactams. So lactams are cyclic amides. What kind of amide is this? Primary, secondary, or tertiary? That is a secondary because we have 2 carbon-nitrogen bonds, but it is a beta-lactam, okay, because we have 2 carbon atoms between the carbonyl and the nitrogen of the amide. So we have a beta-lactam. You can also have gamma-lactams. My group has worked in the area of gamma-lactams a little bit over the last several years. They turn out to be fairly interesting molecules. What kind of amide is this? That is a tertiary amide. Even though it is a gamma-lactam, it is a tertiary amide. Can we have primary lactams? We cannot, right, by definition, because they got to be part of a cyclic structure. So we have beta, we have secondary and tertiary, but we can't have primary lactams in that structure. Now we're going to talk a little bit more about this for my biological friends in here. Beta-lactams, anybody know what beta-lactams belong to? Antibiotics. So the beta-lactam antibiotics, anybody know what the famous one is? Penicillin, right? And penicillin is very useful. It's also considered a last line of defense. When I was a young kid, you got a shot of penicillin every time you got sick. Many of you have probably never even taken penicillin, and the reason is because we don't want it to develop, we don't want additional bacterial resistance to be developed, and so they only give it as a last line kind of defense sort of thing these days, okay? It turns out that there are a lot of bacteria out there that have gotten smart to penicillin and have developed, have evolved mechanisms by which they can deal with it, okay? Nitriles, okay? Nitriles, well, wait, I thought we were talking about carboxylic acid derivatives. Why would a nitrile be in the same talk as a carboxylic acid? That doesn't look anything like a carboxylic acid in terms of its structure, right? That's linear. It's sp hybridized. It's not sp2 hybridized. Why is it in the same category for functional groups, though? Okay, so this carbon can be an electrophile just like the carbon atom of a carboxylic acid derivative can be an electrophile. That's a good point. What else? Resonance. No, I can draw different resonance structures. Not a bad thought, though. What about the oxidation state of these two carbons, this carbon and this carbon? They're the same. They have the same oxidation state. And so it turns out that they place nitriles in the same category as esters and lactones and other derivatives that we'll be talking about. Okay? So we have already determined, somewhat painfully, that these are not actually strong acids, right? When we think of strong acids, we think of things like nitric acid, sulfuric acid, hydrochloric acid, hydrobromic acid. We know that when we place a strong acid in water, it completely dissociates into its ions, right? If I take nitric acid and I place it into water, it's going to completely dissociate into hydronium and nitrate, by definition, because it's a strong acid. Okay, the equilibrium lies so far to the right that we consider the reverse reaction to be negligible in water, right? However, that's not true for a carboxylic acid. It will actually have a true equilibrium. So when we place carboxylic acid in water, it will be in equilibrium with its counterions, or carboxylate anion and hydronium. So if I take a carboxylic acid that's not soluble in water, let's say we take benzoic acid, what's the structure of benzoic acid? Benzene ring, yep, benzene ring with a carboxylic acid on it. Okay, how many carbons does that molecule have? 7. So, and how many hydrogen bonding groups does it have? 1. So does it fit the rule for solubility in water? It does not. It's above that. What's the rule? 5, right? So it's 2 above that. So it's not terribly soluble in water. So if you take benzoic acid, you pour water on it, you got this white fluffy stuff that's sitting there not seemingly able to dissolve in water. But then Jack comes along and starts taking an eyedropper full of sodium hydroxide and he starts adding it to the water, and all of a sudden that white fluffy stuff starts to looks like it's dissolving in the water. Why is that? I'm pushing the reaction to the right because hydroxide reacts with the carboxylic acid to make the carboxylate. And why does that matter? Why should that be more soluble in water? Pardon? It's charged. It's a salt. What do we know about salts? Sodium salts. Huh? They're more soluble in water, right? They typically dissolve in water. Okay? So we can actually extract the carboxylic acid into water, right? And then we can take the carboxylic acid and we can get it back by treatment by protonating it, right? So what kind of acid would we use? Give me an example. What did you do in the lab when you did the extraction last semester? This is how you separated your carboxylic acid from your neutral? Used a separatory funnel? I think some of you had benzoic acid. What's a convenient strong acid that you typically use in the lab? Sulfuric would work. It's probably not the one you used here, but it would work. Nothing wrong with it. Hydrochloric acid is the one that we typically use, right? So you place this in hydrochloric acid, you get the acid back, and you can isolate it, right? Anytime we can convert something into a salt, that rule of 5 gets fuzzier. The rule of 5 really only applies to neutral molecules that have hydrogen bonding groups. Once you've converted that into a salt, either a negatively charged salt or a positively charged salt, okay, that rule kind of goes away, that rule of thumb. Okay, so you can take something that may have 8 or 9 carbons and get it to go into solution pretty easily by converting it into a salt. Now, you can't take something with 100 carbons and just put 1 charge on it and make it soluble, okay? But you can extend that rule of 5 by making salts, okay? So this is what you all did in lab. You all had a group, and you did that pretty easily, okay? So we know that we generate an equilibrium, and how can I push the equilibrium to the right? How can I make the acid stronger? In general, what do I have to do to push the equilibrium to the right? I could, but water's pretty concentrated, so I'm really not going to change the concentration of water much, right? I could add some base. Okay, what else can I do? In general, keep it general. What do we have to do? Heating it up may or may not. Fundamentally, what do I have to do to push the equilibrium to the right? Make the acid weaker? Oh, you mean this acid weaker? Well, if I look at it, that's H3O+. That's a strong acid. So regardless of what this is, I'm always going to get H3O. So I really can't change that. But what can? I can make the conjugate base weaker what? A weaker base or a weaker acid? Yeah, that's right. So I can stabilize the anion, right? Anything that I can do that stabilizes that anion is going to push the equilibrium to the right. Remember, it's all about the conjugate base, right? Conjugate base stability. And one way to do that is to add groups onto the carboxylic acid that stabilize that negative charge, right? So if we have a group, that's what G stands for here, okay? We have some type of group that is attached to the carboxylate that is electron withdrawing. What's that going to do to the anion? Stabilize it or destabilize it? It's going to stabilize it, and so it's going to push the equilibrium to the right, right? If I add a group that donates electrons to the carboxylate, does that stabilize or destabilize? It destabilizes, and it pushes the equilibrium to the left, right? So we can change the position of an equilibrium by what substituents are actually on the carboxylic acid functional group. So let's look at the example. We've seen this before when we were back in chapter 3 or 4, whenever we were talking about acids and bases in organic chemistry. So here we've got an example. This is acetic acid. The pK is 4.75, 4.76. Okay, this slide goes with 4.76. Now notice what happens as we go to the right. What's happening to my pKa value? It's going down, which means the acidity is going up, right? 0.7 is getting pretty darn close to being a strong acid. It's not quite yet, right? But it's getting there. So we're going from something that's quite weak to actually something that's fairly strong. Okay, so this molecule is actually going to dissociate substantially in water to give the carboxylate. What am I changing as I go from left to right? Okay, I'm substituting what for what? So I'm taking away hydrogens, and I'm adding electronegative atoms, right? And so which effect was this? This is the inductive effect. Many of you confuse it for the element effect. Why is it not the element effect? That's right. So we have to look at the conjugate base, and the element effect is about what element bears the formal negative charge, right? Here, that's always going to be oxygen in all four cases, right? But what is changing is the atom or the substituent, right, that is attached to the alpha carbon, okay? Now, that's a pretty strong effect. For each unit of pKa, that's the equivalent of what? Mathematically, what is that equivalent to? So a pK of 1, a pK of 2, what's the difference? Is it really just a 1 difference? It's logarithmic, right? So it's a difference of 10, right? I mean, that's, you know, every unit you go is an order of magnitude, 10 to the whatever power, right? So that's pretty impressive change just by replacing some hydrogens with some chlorine atoms. Now, we can also look at placing the chlorine atoms. Here, they were always placed at the alpha carbon, but we can also place our chlorine atoms at the alpha, the beta, or the gamma carbons in something that has more carbons, or even further out, right? And what do we notice about the pKa there? I've not changed the number of substituents, right? What have I changed? I've changed the distance. And what do we remember about the distance relationship in the substituent effect? Falls off quite dramatically with distance, right? So at the alpha position, right, so that would be very similar to this one, right? Notice the pKa's are almost identical. Okay, this one's a little bit lower. I'd say that's within the margin of error. But if I move the chlorine from here and swap it with a hydrogen that's here, notice what happens now. Where are we getting closer and closer to? Up here. We're getting really close to the pKa of the unsubstituted carboxylic acid, right? And then when we go out to the gamma position, then we're even closer, right? So the further away we get, the less and less it behaves as if it is substituted, right? I was going to say substituted, but that's not even a word. So the substituent effects have a big role to play. We also know that substituents can have a big role to play in the benzoic acids, okay? So if we look at nitrobenzoic acid, chlorobenzoic acid, benzoic acid, and methylbenzoic acid, we can see quite a difference in pKa's here. So here's the unsubstituted benzoic acid. Can anybody tell me why benzoic acid has a lower pKa value than acetic acid? Yeah, so we've got the aromatic ring that can help, in a way, kind of function like an electron-withdrawing group in and of itself. And here we've placed on a chlorine, and we see that the pKa has dropped down. Here's the nitro. The pKa has dropped down quite a bit. Methyl, the pKa has gone up. You know, we can measure that, right? So this is an electron-donating group. These are electron-withdrawing groups, and we can clearly see the effect of these groups on the pKa of the resulting carboxylic acids. Not as big a difference as we see with the aliphatics, but nonetheless, we can still see the same type of trend. Okay? So let's talk for just a minute how we can make some carboxylic acids, right? We've talked about this already, so this is kind of review. We can take alkenes and we can oxidatively cleave them to make carboxylic acids. Here we're using ozonolysis. So if we use ozone followed by some oxidative workup like hydrogen peroxide, this will make carboxylic acids. What would we get if we used ozone followed by zinc instead of H2O2? So if I put zinc here instead of peroxide, what would we get? Would we get carboxylic acids? What would we get? Aldehydes. In this case, you could get ketones, but in this case, you're going to get aldehydes because of the hydrogen that's attached here, right? Now remember I told you that potassium permanganate, right? What did we learn that potassium permanganate would do if it was kept cold? What did we get? To an alkene? Yeah, so we got a diol, right? So if we kept potassium permanganate cold, we got a syn or trans diol. Yeah, so you get a syn diol. However, I told you that it was tricky, and that's why we needed the osmium tetroxide, right? The reason it's tricky is because if it gets too hot, this actually over-oxidizes and gives you 2 carboxylic acids. Okay, that's quite common, is that you'll take an alkene, you'll treat it with potassium permanganate, and if it gets too warm, it actually gives you 2 carboxylic acids after workup. Okay? If you keep it really nice and cold, and you're careful, you can get a diol, but that's kind of tricky to do. Okay? And so you can actually oxidize these alkenes and break them apart into 2 carboxylic acids. You can also oxidize aldehydes. So we've learned that if you take a primary alcohol and you use Jones reagent, for example, you get carboxylic acids. And we learned that that actually goes through an aldehyde. So Jones reagent oxidizes the primary alcohol to an aldehyde, which then continues to oxidize it all the way to the carboxylic acid. Okay? So you can take primary alcohols or aldehydes and use Jones reagent or Jones type reagents and get carboxylic acids quite easily. There's another reagent that we can use that takes aldehydes and converts them into carboxylic acids. It's called Tollens reagent. You need to know that one by name. I'm actually going to do a demo later on, maybe this week, where I show you the Tollens test because it's kind of neat. We'll talk about it on the next slide, but I'm going to show you the demonstration in class. And it is very selective for taking aldehydes and oxidizing them to carboxylic acids. The only problem with it is you have to use silver. What's the problem with using silver? It's kind of expensive. It's kind of a pricey reagent to use, right? Because we like to put it in jewelry and wear it around our necks and other things. So it's kind of pricey. It's not as expensive as gold or platinum or anything like that, but it's still a fairly pricey reagent to use when you have to do this. Okay. So this is what the Tollens test is. Okay. And don't worry about the top yet. We're going to talk about that in just a minute. But the Tollens test takes a aldehyde, okay, and you treat it with the Tollens reagent, which is under basic conditions. So you've got this silver ammonia complex. You've got hydroxide around, okay, and you're taking the the aldehyde, and you are oxidizing it basically to a carboxylate. Not to a carboxylic acid yet because we're under basic conditions, right? But nonetheless, the oxidation state changes for this carbon, right? So how would we calculate the oxidation state for this carbon? What's the oxidation state of this carbon right now? How many electrons does carbon come in with? 4, right? And so how many does it form, or does it own now? Not formally. We're not talking about formal charge. How many does it own? It owns 1 from here, right? How many from the hydrogen? It owns both of those. Does it own any of anything? It doesn't. So when we do that math, it's a 4 minus 3 equals 1, right? So it's in the +1 oxidation state. When we oxidize it using Tollens reagent, now what's the oxidation state? Comes in with how many? 4. How many does it own now? 1. So it is in the +3 oxidation state, right? So you go and do those types of oxidations pretty easily. But what's really kind of cool about this reaction is the fact that you get silver metal out of this, because it's getting what? It's getting reduced. The aldehyde is the reducing agent. The silver is the oxidizing agent. You get this silver mirror. Now what I'm going to do in the demo, I'm going to take a flask, about 125 milliliter Erlenmeyer flask, and I'm going to put sugar in it. And I'm going to put some Tollens reagent in. I'm going to sit here and I'm going to shake it while I talk to you about it. And all of a sudden it's going to become a nice shiny silver mirror. Okay? This is how people, when they make custom Christmas ornaments, will silver them. They use the Tollens reagent. Okay, it's kind of cool. If you have a real high quality mirror, and I mean an expensive mirror, they use silver to give the reflective surface. They don't use the cheap stuff. Okay, and they will actually use a process very similar to this to make high quality mirrors. Okay. Now, how can I take a sugar, right, and use it when the Tollens test needs an aldehyde? What's this functional group? It's a hemiacetal. What does hemi mean? Half, right? What's an acetal? Remember we used it in like ketones and aldehydes to protect them? How did we make acetals? So if Jack wants to protect his ketone, right, from a Grignard addition, how would he protect it as an acetal? What would you react it with, Jack? There's no real reduction going on. So I'm taking a ketone and converting it to an acetal. What would that look like? It can be a ring if the alcohols are on the same molecule, right? Remember we took alcohol plus ketone and we got an acetal. So we replaced the carbon-oxygen double bond with 2 carbon-oxygen single bonds, right? We got rid of the pi bond, basically, right? So this is a hemiacetal, meaning that it's got 1 ether-looking like linkage and 1 OH, okay? It's half of an acetal, okay? Now, this is an equilibrium with the open form. And sugars do this when you place them in water. So when you eat sugar, simple sugar, okay, something like glucose, it will actually be in equilibrium with the closed form or the hemiacetal form and the open form, okay? Has anybody ever heard that sugar's toxic? It is, okay? It's actually, some people consider it quite poisonous, actually. Tastes really good. Okay? But it is quite harmful because it can open up into this reactive species that can actually react with a variety of molecules in your body. Sugars react with all kinds of things, okay? And it's because of this open form, okay? The open form, what's the functional group? That's an aldehyde. Aldehydes react with the Tollens reagent to give silver and a carboxylate. So we're going to take sugar, we're going to take the Tollens reagent, we're going to convert the sugar into a carboxylate, and we're going to make a silver mirror on the flask. And what I'm going to do is on the next exam, whoever gets the highest exam score gets the flask that's silvered. Okay? And if there are multiple people with the highest score, I will make more. Okay? So you'll get about 10 cents worth of silver from me. Okay? Not a lot. It's a very thin layer. Okay? But that's the incentive for the next exam. Okay? You can get the silver flask if you get the highest score on the exam, okay? But it's very selective, okay? This doesn't mess with ketones, it doesn't mess with amines, it doesn't mess with alcohols typically, okay? There's all kinds of alcohols on a carboxylate, or excuse me, a carbohydrate, and so we can go in that direction. All right, so we can synthesize carboxylic acids by the hydrolysis of nitriles. So for example, if you take this nitrile and you treat it with a base followed by workup with acid, you can actually convert the nitrile back into the carboxylic acid. Okay, so this is going from valeryl nitrile to valeric acid. This reaction you know is occurring because this stuff stinks to high heaven. It's not pleasant to be around. And so the reaction goes, at least on paper, quite easily. And we know that we can make nitriles quite easily by what kind of reaction would this be? That's just a generic SN2 reaction. So, right, we can take sodium cyanide, we can take an alkyl halide, we can make the nitrile, and then we can take the nitrile and convert it to the carboxylic acid. I want you all to know that I said this is really on paper, okay? Yes, this can happen. But in practical world, this doesn't work very well. I've tried to do this exact reaction 5 different times in my career, and I've only been able to get it to work halfway once. Okay? it just doesn't work very well. You typically need to boil this for a long time, put it under high pressure. There is research where you actually can add catalyst to make this work a little bit better. It's really not as easy as it is on paper, okay? And so these nitrile hydrolyses, in my mind, are really not particularly practical, okay? They just require too much time and too much effort to get them to work. And so there are other ways to make carboxylic acids that are actually much more practical than this, okay? So for example, we can take alkyl halides and we can convert them into carboxylic acids by converting the alkyl halide into a Grignard, followed by reacting that with carbon dioxide. Now I think you all do your Grignards this week, right? So you're going to make a Grignard, but you're not going to react it with carbon dioxide and make a carboxylic acid. You're going to make I think you guys react it with a ketone and make a tertiary alcohol, if I recall right. But nonetheless, you can take this and do this chemistry fairly easily. So here's an example where you take this trimethylbromobenzene, react it with magnesium ether, you make the Grignard reagent, and then you add carbon dioxide, followed by acid workup, and you can get the substituted benzoic acid fairly well. These reactions depends on how you add the carbon dioxide, whether or not they're going to be effective or not. So what do we know about carbon dioxide? How could I add it? I could bubble it through because it's a gas, right? But that's kind of a trick because you got to make sure it's dry. So how would I make sure that a gas is dry? Make it hot. So if I take gas and I put it through an oven and then bring it out the other side, wouldn't the water just come along with it? I mean, how would I separate gaseous water from carbon dioxide? That can be kind of tricky. So what would I need to do? I could do that. That's going to be a lot of work, though. I could do that. I could do it. Or I could take the gas and I could bubble it through something that dehydrates. What do we know that dehydrates really well? Magnesium sulfate does dehydrate, but it's not really that good at dehydrating gases. It's really good for like your ether layers and stuff like that. What else have we learned that's a really good dehydrator? What did we use to dehydrate alcohols to make alkenes? Concentrated sulfuric acid. So actually what you do is you first bubble carbon dioxide through a solution of concentrated sulfuric acid. That takes out any water that's in the carbon dioxide. And then you have to pass it through something else to make sure there's no acid components coming through, and you could do it. That's kind of a pain. So really what we typically do is we go over to the science storeroom and we buy some dry ice, and we crunch it up into a powder, and we just add it slowly as a solid and get this reaction to occur. But when you do that, even the yields are fairly low. It's actually better if you do it with the gas. The yields are fairly low because the carbon dioxide is so cold that it freezes water on the surface from the air, and so you can never really get it completely dry. Okay, and so there's some practical issues with doing that chemistry. Okay, so we've learned that we can take a carbonyl group, we can add a nucleophile to it and make an alcohol. So here we had a ketone or an aldehyde depending on what R and R prime are, right? So describe this mechanism for me in words. What's happening? What's the nucleophile doing? Why the carbonyl carbon? Pardon? It's electrophilic. We are going to break the weak pi bond, but I could break the weak pi bond by also attacking the oxygen, right? So why does it attack the carbon? Why is it electrophilic? No, you're right. The oxygen is what?
The oxygen is withdrawing.
Yeah, it's withdrawing electrons to itself, and so we have a partial positive charge on the carbon and a partial negative on the oxygen, right? And so the nucleophile attacks, we break Anna's weak pi bond, we get the carboxylate, which is also known as a tetrahedral intermediate, and then upon workup, we get the alcohol, right? That is a simple addition to a carbonyl. Would we expect the same thing, at least initially, to happen in the reaction of nucleophiles with carboxylic acids? So if I took acetic acid and I threw in a Grignard, would we expect that chemistry to occur? Yes or no? It's too basic. That's right. So typically, a carboxylic acid will react with the nucleophile before the nucleophile can even attack the carbonyl, right? So carboxylic acids rarely do this type of chemistry. There are examples, okay, but they rarely do because the acid is just too acidic and the nucleophiles are typically too basic. However, the carboxylic acid derivatives, do we have the acid, acidic hydrogen? No, swing and a miss. No. Okay. So if the X here is some kind of leaving group, something like a halogen, for example, let's say the acid chlorides, okay? There's no acidic hydrogen on this atom. So the nucleophile will simply attack the carbonyl carbon and break that weak pi bond. And we get the same tetrahedral intermediate that we had up here, okay? But now, let's say chlorine. Chlorine is a fairly good leaving group, right? And so what happens is the tetrahedral intermediate collapses and the leaving group leaves. And we've just done an acyl substitution reaction. This is exactly the reaction that is occurring in biological systems. The only difference is biology can't work with acid chlorides. So there are other types of acyl groups, other types of leaving groups that we use in biology to do this type of chemistry. This is called an addition-elimination mechanism. So we have the addition to the carbonyl, we have the tetrahedral intermediate that then collapses back to the carbonyl, okay? And so this is how biological acyl transfer reactions work. So when you get into biochem and they start talking about acyl transfer reactions or acyl substitutions, it's all this. This is what's happening in the enzyme active site. The enzyme just facilitates the reaction, okay? You will have biological molecules, though, that are attached here for X to make it compatible with biology. If you had acid chlorides floating around in your blood, the pH would be too low and you'd die. So biology has had to overcome that problem by creating leaving groups that are compatible with the pH range of a biological system, okay? So you can take acid chlorides, you can take esters, you can take amides, and you can do this type of chemistry, okay? It's pretty straightforward kind of stuff. So an acid chloride plus a nucleophile generates a new nucleophile carbon bond that happens to be part of an acyl substitution. These reactions are actually quite quick. This is the type of reaction that you guys can go into lab and in 20 minutes you'd be done. You'd be spending more time in pre-lab work and in working it up and getting your spectra than you would be actually running the reaction. The problem with running these reactions in the lab with acid chlorides is that hydrogen chloride is the byproduct. And HCl is a gas. It will come out of the reaction mixture and it will choke you quite badly, okay? And so typically these reactions are actually run in pyridine. So pyridine will react with the generated HCl and form the pyridinium salt. And so you got to deal with purifying this at the end. But these reactions are very, very quick and easy to do, okay? What else did we use acid chlorides for? What other named reaction? Friedel-Crafts acylation, that's right, okay? So I can take an acid chloride and I can react with all kinds of nucleophiles and I can get all different kinds of new functional groups. So an acid chloride plus a carboxylate gives me a, what's this one? An anhydride. This is the easy way to make anhydrides. You take the salt of a carboxylic acid, you take an acid chloride, you mix them together, you get an anhydride. I can take an acid chloride, I can react it with water, and I get a carboxylic acid. I can take an acid chloride, I can react it with an alcohol, and I can make an ester. You all made an ester last week. Some of you were supposed to have made an ester last week, right? You all did not use this process. What process did you all use? What was the name of that reaction? Fischer esterification, and you need to know that for this exam, okay? You covered it in lab. But Fischer esterification. Why is Fischer esterification more practical for you all than using acid chlorides? What did you all use for the Fischer esterification? I know spring breaks happened in between, but what did you all use for Fischer esterification? What were the functions? What starting materials did you have? You took benzoic acid, and you used what? Methanol, and you put them together and nothing happened. You had to add something else. What else did you add? 5 drops of sulfuric acid. That's right. Okay, so it was an acid catalyzed process. It doesn't go through acid chlorides, okay? But it forms the same type of product. All right, I'm going to stop there for today. I got some stuff.